So what we're going to do is going to have a look at our we're going to have a look at graphs and what happens when we translate them in some way. So and this is graphs of functions. So for example, if I had y is equal to some function of x, if you're unfamiliar with functions, just think about it as an expression of x. An expression could be, for example, so f of x could be maybe x squared, or maybe it could be that. It could be just x, for example. It could be 2x, could be 2x minus 1. It could be all any number of things. But the point is, it's just some expression of x. And what we're learning, the point of functions, is to show how no matter what the expression is, there are certain patterns that we can notice about it. So if we start off, in fact, this is going to combine very closely with completing the square. So if we started off with saying f of x is x squared, and we said y is equal to x squared. So we know the graph of y equals x squared is, it looks like that. So what we're now going to have a look at was what would happen is, what would happen if I did y is equal to f of x plus 1. Okay, so I'm going to, underneath the original equation, I'm going to write y is equal to, instead of doing x squared, I'm going to do x plus 1 squared. As you can see, it's shifted to the left. Okay, and we're going to try doing what is it when, I might get rid of some of these things now because it's going to be distracting. Oh, not that. I want to get rid of that. Yeah. Okay. So if f of x is equal to x squared in this case. So now we're going to say, well, what is it if I do y is equal to f of x and then add 1 outside of the bracket? Well, that would be just, let me see if I can I move that? Yeah, oh, that's good. Okay. So this time it's going to be y is equal to x squared, so just as normal, but then I'm going to add 1. So when I add 1, it goes up, and when I add 1 inside the brackets, it shifts to the left. So that's kind of weird because when I put it inside the brackets there, it goes to minus 1, but outside the bracket, it just goes to 1 there. So we can combine these now. So I'm going to turn off the green and the blue because otherwise there'll be too much stuff on here. And I'm going to go, this time I'm going to just put it together bit by bit. So this time I'm going to do x plus 2 all squared. So it shifted 2 places to the left. And if I did it, in fact, if I did it x minus 2, it shifted 2 spaces to the right. But then I'm also going to add 1. So now we can see the relationship with the completing the square formula. So y is equal to x plus, what letter shall I use here? W. So we got it. I can't put a because we know a, b, and c are taken in the quadratic formula of ax squared plus bx plus c. So we'll use some other letter, and then we'll put plus. I don't know, what other word shall I use here? M. Why not? Okay. So actually, I use M and N for other things. I'm going to put U. Okay. So this value here is, in fact, what I can say is the x movement. Well, I'll put horizontal movement. The horizontal movement is equal to negative w, right? Because this flipped the sign. We've got negative 2, negative 2 is positive 2, and as you can see, it went 2 spaces to the, it was translated by 2, by +2, because it went to the right. And then the vertical movement was just equal to u. So, and now the thing about that is that normally x squared, the point at which it touches the 0 axis is the turning point, or the minimum point. Okay, if it's just x squared, positive x squared is negative x squared would be the maximum point. So that means that when we shift it to the right by 2 spaces, or by negative w spaces, and up by u, then this new minimum point here is going to be equal to negative w and then u. These aren't official symbols at all. So one of the reasons, probably the most common reason for completing the square is to find the turning point. Okay, if we expand this, if we expanded out the purple equation, we got so y is equal to, we've got x minus 2 multiplied by x minus 2, so that's going to be x squared. It's going to be minus 4x, then plus 4, and then we've got to add the 1. So x squared minus 4x plus 5. Hopefully, if I've not messed that up, when I write that equation down, y is equal to x squared minus 4x plus 5. It is exactly the same equation, because you can see it's gone over the top of the previous graph. So the black equation, this 5 determines the y coordinate, and the purple equation, this the negative 2 and the 1 determine the minimum point. Now, we don't actually have, I've accidentally picked ones where we don't really actually have an x-intercept in this case. So this is also a follow-up question in this case might be, why can't this be solved? And you'll because if you can use you can actually prove that it can't be solved by taking so for it being equal, for the y is the no x-intercepts, or let's say this is all equal to 0, why can't it be solved? You'd have something like x minus 2 all squared is equal to negative 1, and you can't square root negative 1, so that's a proof that it can't be solved. And when we look at a graph, it doesn't go through the x-intercept. So I just wanted to, that's kind of like, I've kind of jumped around a little bit. I'm kind of showing how it works with functions, and also how that links in with completing the square. But just to, hopefully not to make it any more too confusing, I want to show you that this is the case with all functions. So what I did, so if I did y is, let me use a different color here. I think I might make it slightly thicker. So y is equal to f of x, and this time x plus w, and then plus u. Before we did, so this is almost like that, where f of x is x squared, and I've changed it. I've kind of translated the function. So if I get the eraser, I'm going to get rid of this. I should have written a squared bit there. Sorry, that should have a square symbol. So what I'm going to do this time, I'm going to turn off these two graphs, and I'm going to write another function. So we're going to say y is equal to, and we'll do some sort of cubic graph. So let's go 3x cubed minus 4x squared plus 3x. Let's do minus 3x. That's better. And then plus 2. That's good. Okay. And then we're going to, this is getting a bit complicated, but I'll just copy all that. And we're going to do it where I'm going to add, let's put add 2 again. Okay, so I'm going to shift it. So I'm going to put W is equal to 2 and U is equal to 1. Remember, this one, the horizontal movement is -2, so this should shift it 2 spaces to the left if I do all this. So I'm going to, each time x has been written, I'm going to plus 2. There we go. So it's shifted, as you can see. If we take that on there, or negative, I think you'd have to get your calculator out, but hopefully you can see that going to be roughly a difference of 2 there. So yeah, that's right, isn't it? Yeah. And then if I were to, at the end of that, add 1, this also shifts it up by 1 space. Okay, so the point is, this works with all functions, but I wanted to see how kind of do 2 topics at once if it's not too complicated, so you can see the similarity. Yeah. Okay, so let's just clear all of those notes. And in fact, I think, I'm just going to turn those off. And I'm just going to do y is equal to sine x. So sine x, y is equal to sine x looks like this wavy pattern. Now, if you know anything about the equation for y equals sine x, you might be a little bit confused here because the numbers don't seem to be quite right. Don't worry about that for now. Let's just imagine that y equals sine x makes a wavy pattern. Y equals sine x plus 1 lifts it up by 1. Minus 1 brings it down by 1. Y equals sine minus 1, shifts it to the left by 1, and plus 1, the first one shifts it to the left by 1. So let me just do y equals sine x. So the green one is shifted to the left by 1 because we flipped the sign of that one in the middle. So, all right, I'll stop the video there and we'll have a quick look at some questions.